We present our work on learning to manipulate object collections using grounded state representations. Most prior work has focused on picking and pushing individual objects one at a time, perhaps in clutter. Instead, our goal is to develop a system to solve tasks that require reasoning about and manipulating many objects simultaneously. Our approach is to train image-based manipulation policies purely in simulation, while exploiting ground truth simulator state information to learn accurate multi-object state representations. For evaluating our approach, we focus on a real-world tabletop pushing scenario where 1 to 20 objects start in various positions on a table, and the objective is to push them into desired goal regions visualized by the red squares. We use a two-phase process consisting of a supervised representation learning phase, followed by a model-free reinforcement learning or policy training phase. During the representation learning phase, the objective is to learn a latent space phi that accurately captures multi-object information. We expect different components of the latent space to capture, for example, how clustered or spread out the objects are, where they are located, etc. We collect a training dataset in simulation while applying domain randomization and using a scripted policy designed to randomly move objects around. At every time step, we record both images and raw object poses. We then use this data to train a pair of 2 encoders to learn latent spaces that capture multi-object information from their respective modalities. One of these encoders is a CNN that consumes RGB images and tries to predict raw object poses, thus learning an image-to-state mapping. The other is a graph neural network, or GNN, that both consumes and predicts raw object poses, thus learning a state-to-state mapping. The GNN is trained, in other words, to auto-encode multi-object state information. For our policy training phase, we build off the asymmetric actor-critic approach from Pinto and colleagues. The idea is to feed image information to the actor network so as to produce a policy that operates in the real world, while feeding state information to the critic network to more quickly learn value functions and aid in training. In contrast to prior work, we develop an asymmetric actor-critic style approach that scales to multi-object settings. To represent the current state, we embed the current image into our CNN-based latent space and feed it to the actor/policy network. And we embed the raw state into the GNN-based latent space to feed to our critic/value network. To represent goals, we always use the GNN-based latent space. Since the GNN representation is doubly grounded in simulator state information via both input and output, it greatly stabilizes learning signals in our critics and in our reward function, which uses state-based representations to compare the similarity of the current and goal states. At the end of training, we have a multi-object manipulation policy that can operate on real-world images. We show a few illustrative policy executions here, and we include more comprehensive real-world experiments in a separate video. Here we show a side-by-side comparison of our full method and an autoencoder approach, trained on image reconstruction. The contour lines and purple regions represent the model beliefs about where the objects are located, for our full method and for the autoencoder respectively. Our full approach eventually pushes all objects into the desired region in both of these trials. In this trial, we see the autoencoder performs well for a while, but ultimately gets confused by a crease in the tablecloth. The trial is terminated as a failure after 15 attempted pushing actions. Though our method was trained only using 10 cubes, it generalizes well to different numbers and types of objects. Here we show it holding up well to a scenario with 20 cubes. And here we show it pushing a single cube, which qualitatively seems easy compared to the multi-object setting, as we argue in the paper. And here we demonstrate the policy working to push a pile of silverware across the table. And here we demonstrate on a pile of crumpled up paper, which has very poor contrast with the background, making the task more difficult. We also qualitatively test the system farther outside its training distribution, using 50 objects, 5 times more than it was trained with. Though the model starts to misrepresent the size of some clusters, it seems to have a good sense of where the clusters are and where the individual outlier objects are. The policy also holds up all right and maintains the strategy of keeping the objects in a large pile and corralling the straggler cubes when they get too far behind. And here we demonstrate on the more difficult case of uniformly distributed objects. We don't evaluate on this task in the paper, as none of the methods were able to consistently solve it. We would bet that adding memory would help so as to handle the sim-to-real transfer better and to remember which actions have already been tried. Nevertheless, our model localizes the objects quite well and demonstrates a good strategy of trying to group all the objects into a pile before trying to push them to the goal. Alright, that's all. See the video description for links to the paper and other supplementary video. And thanks for watching.